So today, I'm going to do just things a little bit differently. I'm going to kind of write things out here. All right. So on Monday, we talked about, there were a few things we talked about. One was we talked about the computational representation of numbers and kind of some of the problems that or not problems, but just things to keep in mind when you have that. Okay, so we had computational representation of numbers. Okay, and their consequences. Okay, and then we also talked about root finding. Okay, and so as far as root finding goes, basically we said, you know, you have some kind of function, and the root finding is we're trying to just figure out, you know, this location here. Okay, this is the root. And so we talked about a few methods, right? We had Newton's method. Okay, and so how does Newton's method work? Okay, so with Newton's method, we would take the we would just pick an arbitrary point. So let's we'll zoom in on this section here. Okay. Let's I don't know. And then, you know, we pick some arbitrary point x sub 0. We evaluate the value right here. So this spot is f of x0. And then we also find the derivative at f prime of x0. Okay. And when we do that, we can take a kind of the tangent line, right? And we do a we do f of x0 divided by f prime of x0. Okay, and that is basically, this is kind of the rise divided by the slope, which is going to equal kind of our run length. All right, so you have this, and then we end up over here, and so this location over here is going to be x1. Okay, and then we iterate. Okay, and so at x1, we go right here, we take another tangent line, and that takes us to you know, right there, wherever it might be, so on and so forth. Okay, and we just keep working until we converge into the root right there. So that's Newton's method. Okay, so begin at x sub 0, find x1 as x0 minus f of x divided by f prime of x0. Okay, and then iterate. So that was one method. Another method, we talked about fixed point iteration, but the other method I want to kind of illustrate here will be the bisection method. Okay, so that was Newton's method, and then we also had the bisection method. Where basically we said, you know, you've got kind of the left boundary and you have the right boundary, and then you bisect and you have the middle, okay? And then so right now f of x on the left is less than 0, and currently right here f of x at the right is greater than 0. So the product f of x left and f of x right is less than 0. So this means the function crosses y equals 0 somewhere. Okay, and then you know, evaluate f of xm. So find the midpoint. Sorry, xm. Okay, and basically, just look at the sign of f of xm. That's really all you need. All you really need is just whether f of xm is positive or negative, okay? And if it's, and you basically keep the pairing, keep either xl or xr so that the f of xm and f of the point you keep have different signs. Okay, so in this case we would keep xm and xr, okay, and then when you do that, this becomes your new you start a new iteration here, okay, and you do the same thing over again, okay? So that becomes your new left boundary and your new right boundary, okay? So this becomes, so this is iteration 1. So this now becomes XL and XR, okay? You find the midpoint. And then, so now we would keep these two sides. Okay, and then so on and so forth. Okay. And you keep zooming in smaller and smaller and smaller. Okay, keep bisecting it. And each time you only have to evaluate the point, your new midpoint, okay? Because you can keep everything else. You can keep all of the other, either the left boundary or the right boundary, whatever it is, okay? And so you keep working through that. All right, so does that make sense for bisection method there? Okay. All right, so, you know, when we talk about root finding, we don't, it's not just for the sake of root finding, okay? That we do have actual interest in this, okay? So, for example, we could have, so, you know, one application is maximum likelihood estimation. Okay, and so this is actually an application of optimization, but there's many applications for optimization. Okay, so we'll say one application for optimization. Okay, and that's maximum likelihood estimation. So what I'm hoping you guys are familiar with MLE. So what is MLE? What's maximum likelihood estimation? What are we doing here? Or are we not familiar with maximum likelihood estimation? We're not. Oh, okay. All right. Well, then I guess I'll have to do some explaining here. Okay. So. Okay, here's a very simple example. All right, let's say somebody says, I've got this special coin. Okay. All right, so this is a special coin. Okay, and it says the way it lands heads is it doesn't necessarily land 50% of the time heads, okay? So you've got heads and you've got tails. Will not necessarily land. Okay, because it's a special coin, right? So anyway, so you want to know, okay, well, what is the probability that the coin lands heads? Okay, well, how can we answer this, right? So what we have to do is we have to, we'll do an experiment. We'll collect some data, okay? Collect data, and so let's say we flip the coin 100 times. Okay, and we get the sequence heads, heads, tails, heads, 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 tails, tails, heads, 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 tails, heads, tails, 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 heads, heads, I don't know, something, okay? Blah, 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 okay? And then you count them up, and then you have basically let's say you get 62 heads and 38 tails, okay? So let's say this is what you get after 100 flips, okay? All right, what we have here, okay, this is the actual output, okay? This is our observed data, okay? And we can ask, what is the likelihood of this data? Or basically, what is the probability? When we have actual data, we'll say what is the likelihood, but it's still a probability, likelihood of observing this data. Okay, or basically, it's still, what is the probability of observing this data? Okay, Well, what is that probability? Can we so let's say if p equals 0.6, then our likelihood of the data, and then we could express this as the probability of I'm going to write capital X, this means our data, and I'm going to do vertical bar. What does that mean? Given p equal to 0.6, right? So the probability of getting our data, if the probability of getting heads, p is 0.6, so p would be, probability of getting heads. Okay, would be what? 0.6 times 0.6 times 0.4. I'm just looking at what my sequence was, right? Heads, heads, tails, heads, heads, times 0.6 times 0.6 times 0.6 times 0.6, et cetera, et cetera, et cetera, right? So this just becomes the product of all of my probabilities associated with each x value from, I guess I would have to go I from 1 to n. Is this okay? And then so what would that end up becoming? That ends up becoming 0.6 raised to the 62 times I'm sorry, not 0.6, 0.4 raised to the 38, okay, after we do our entire sequence. Okay, and so this is the likelihood of our data for this particular parameter, for this value of p. Okay, so this is the likelihood of our data if p equals 0.6. Is that okay? So this is the likelihood. Now, if we wanted to generalize this and say, okay, well, what's the likelihood of our data for any value of p? What would we then say?
Well, we would say probability of x given p equals some general variable.
Yeah, okay, so okay, well, before I flip the slide, I just want to make sure everyone's okay with what I've got written up here. Are there any questions here? So we're talking about just the likelihood of observing our data. Okay, this is, yeah, I think the coin flip example is kind of the simplest I can think of here. And so, kind of in general, in general, for our coin flip example, okay, we would say the likelihood, this is L, okay, or our likelihood, will equal the product, or basically, I guess we could say probability of our x given some value p will be the product of p of x, okay? And this is going to become p raised to the 62 times 1 minus p raised to the 38, okay? Whatever that turns out to be, okay? And so what maximum likelihood estimation says is, here, I'll write this out. Says that we should estimate p so that p to the 62 times 1 minus p to the 38 is the largest possible value. Okay, so we want to maximize, we want to pick a parameter p, a value of p, so that the probability of observing our data is as high as possible. Okay, and that makes sense, right? Because the fact that we observed this data indicates that we observed it, and so we want to say, well, what's the probability of observing the data that we got? That should be as high, we want to make that as high as possible, okay? Because otherwise it would not make as, it would make less sense for us to say, well, you know, we should make this observance unlikely or something like that, okay? So we want to estimate our p so that it should be as large as possible. And in our coin flip example, okay, you know, if we were to graph this and find the maximum of p, then, find the p that maximizes this, okay, so in this case, in this example, you know, the likelihood function is maximized when p equals 0.62, okay? And so this would match our intuitive sense that that if we flip the coin 100 times and we get 62 heads and things like that, our maximum likelihood estimate will be so that p is equal to 0.62. But we could, you know, we could graph this. This is just a function of p, right? And we could see, like I could fire up R and we could see where p is maximized, and so so we can just say L is going to be a function of p, and what it's going to return is it's going to return p raised to the 62 times 1 minus p raised to the 38, okay? And then we can say, so p is going to be sequence from, we'll say 0 to 1 by equals 0.005, and then we'll say f will be, we'll take L of p, right? And then we'll plot p versus f. What is it? LTY equals L? Or is it type? I forget. Okay, so this is what our function looks like. Okay, and so maybe we want to just zoom in right here from 0.5 to 0.8. Okay. And so we can see kind of where it's where our function is getting maximized. So let's zoom in further, 0.6 to 0.65. Okay, and then so here we can see that it is indeed maximized somewhere around 0.62, or it is at 0.62, our maximum value. Okay. Is this okay? All right, and so I mean, and so that's a very simple example where you know, we're trying to, we would like to maximize this function. Okay. You know, there are other examples. So let's say you have you know, let's say you've got some population that's normal. Population we assume to be normal. Okay. and then you know, you draw observations, so you get and your data has you know, different values here, right? You know, 125 and 146 and 103 and 190, etc., etc., etc. Okay. So then you want to, like, you know, what is mu, or what is sigma? And this is a little bit more complicated because now we have two parameters here to figure out. Okay. And so we can say, you know, what is the probability of observing 125? Okay. So you would need the can I write this as the density for the normal distribution? This is kind of our normal density. So we would say, you know, so the probability of getting 125, we can write as 125, and you know, I guess it should be either you can. So in textbooks, they might have the vertical bar, or they might write a semicolon. Okay, you also see it written this way. So this is basically, what is the probability of getting 125 if mu equals mu and sigma equals sigma. Okay. And then so the likelihood of our data will be what? It's going to be the product of basically all of these things, of 120, not 120, I'm sorry, the product of all of our x values given the value of mu and sigma that we choose. Okay, so we would say, you know, what's the probability of getting 125, and the probability of getting 146, etc., etc., etc. Did I mess something up, or is it okay? All right. And okay. Does that make sense? Okay, and then so we would get some kind of function here, okay? And because it's you know, normal is a part of the exponential family, there's some nice properties, and we can solve these things, okay? And anyway, so we get the likelihood here. You know, most likely we would probably use the log likelihood, so we don't have to deal with the product, but rather as sum, okay? And then so you'll often see L, and then this will suddenly turn into kind of the log of the likelihood. And this is going to become the sum of basically log of all of this stuff, okay? And then we want to maximize this, right? And we basically find mu and sigma so that it maximizes the log likelihood. Okay, and so that's an application of our methods here. Okay. The linear regression is also, or regression in general, is a optimization problem as well. We're trying to minimize the sum of squared residuals, okay, by altering our intercept and our slope. Okay, so another application. right? So, you know, you've got some data here. Okay. And we get all of these residuals. Okay. And so we have y hat is equal to b0 plus b1x, all right? And we want to pick b0 and b1 so that the sum of the residuals y minus y hat squared is minimized. Okay, and then so we'd have sum of y minus b0 minus b1x squared. Okay, and we try to minimize. Pick b0 and b1 to minimize. To minimize that. Okay, and so here we have, so at this point, the y and the x's, so in this thing, the y and x's are now fixed. Fixed values, and we vary b0 and b1 to minimize the sum. So these are all applications of optimization. Okay, we're trying to find ways to either, you know, maximize a certain function to get the maximum likelihood estimates, or we're trying to minimize this. We might call this a loss function or an objective function. Okay. So to kind of figure out our parameter estimates. Okay, and you know, in future courses, you know, we can apply this to, you know, more complicated situations, such as like in machine learning, you want to what they might say, train a neural network. Okay, so a neural network is this setup where you have an objective function as well, and you want to minimize the value of that objective function, and it's an optimization problem. Okay, at the heart, it's an optimization problem. Okay, and so here we're going to just start covering just some very basic ideas in terms of how we can do optimization on the computer. Okay, and so well, let's see, it's 9:50. Why don't we take a short break, a 10-minute break here, and then we'll come back and we'll start talking about how optimization can be done.